Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am very happy to have Eugene Chiang with us today. Hello, Eugene.
Hi, Frank. It's good to be here.
It is an awesome day on this October 30th of 2024 as we record this, one day before Halloween. So looking forward to that one. I am actually a little bit. And Eugene, what is your geolocation?
Oh, I'm here in the Bay Area,
Oh,
uh, at home actually.
yes.
But today's
Fall in
one of
the
my
air?
work
Is
from
fall
home days.
is
Yes.
fall in the air in the Bay Area?
Oh yeah, no, it's really great. California is not known for its foliage, but per se, but I see some colors changing
Very
in the
cool.
neighborhood trees. So it's really nice. It's one of my yes, probably my favorite season.
Yeah, yeah. I think October is the best season in California, in my opinion. So, yeah.
Yes.
So I'm in Phoenix, and we are definitely starting to cool down. In fact, we got down to about 56 Fahrenheit this morning, which is a low for us. We will get up into the lower 80s today, but very pleasant as we have gone past equinox. So very nice. Yeah. And Eugene, what do you like to do for research?
So I'm in theoretical astrophysics,
Okay.
with an emphasis on planets. Almost everything that I work on has to do with planets in all aspects. I would say formation, dynamics, atmospheres. If one is interested in formation, one has to be interested in star formation as well.
Yes.
Planet formation being an extension of star formation. So disk processes, accretion disks, um, and planetesimal formation, which I think will be the subject of today's discussion.
It is. So speaking of formation, let's go ahead and get into this very lovely article. This one is an APJ letter. It is open access. It's the open access era, people. You can go get a copy for free. Go get one. Cavitating bubbles in condensing gas as a means of forming clumps, chondrites, and planetesimals. And Eugene, take us away.
Okay, well, thanks again for the opportunity. This is basically what I worked on, what I did last summer, just this past summer.
Or here we go.
This is what I have to report
Oh,
for
very
for
cool.
my summer activity. It was enjoyable. It was enjoyable process.
Mhm.
Um, so the project had to do with chondrites, which are, as people may know, the most primitive meteorites that we have.
Mhm.
Um, 80% of the rocks that fall from the sky, I am told, are filled with millimeter sized or sub-millimeter sized igneous spheres,
Yes.
uh, called chondrules.
Mhm.
Super surprising. I mean, who would have thought?
It is.
Uh, uh, Sorby, I think, was the person who discovered them 19th century,
Yeah.
referred to these little BBs as droplets of a fiery rain. I
Nice.
think is an apt description.
Yeah.
And it's been when people talk about, they're the oldest things that we have. When people talk about they say, oh, the solar system is 4.567 billion years old. Where does that number come from? Well, it comes from the radioisotope dating
Yes.
of the constituents of these chondrites. The
Yep.
oldest being the calcium aluminum inclusions, but the next oldest
Hmm.
being these chondrules.
Yep. I'm with you.
And yeah, so they're the first, arguably, the building blocks of planets.
Mhm.
So, on the way from micron-sized dust grains to megameter-sized planets,
Yes.
one argues that they have to pass through this intermediate size regime of millimeters to centimeters. And somehow, uh, they were molten in the process. They were flash melted.
Huh?
And they had to have been molten because in in space, because they're round.
Right.
So these little round spheres molten in space, and then surface tension would pull them into spheres.
Good. Yes. Not gravity.
So
Not gravity.
yeah, yeah, that's right. So um, big mystery, right? A lot
Yes.
of people have worked on this.
Many
Uh,
of it.
I
Hmm.
learned about this problem in graduate school.
Okay.
Been thinking about it off and on over the years. Uh, I would say they pose two problems, at least.
Okay. At
The
least.
first being how do you melt them,
Okay.
which I think there's been a lot of discussion about. And then the second problem, after you melt it, how do you collect these molten spheres into chondrite parent bodies? And you
Indeed.
have to collect them with incredible efficiency
Yeah.
because the volume filling fractions of these chondrites, the percentage of the volume occupied by these little spheres is order unity. It approaches 100%. So whatever collected them had to have done it with, it was an incredible filter, right? I mean, it just you just have to collect these
Not
uh
miss.
almost without loss.
Right. Not miss them. Uh-huh.
Yeah. Um,
Which is,
so and this problem of collection is the one that I tried to address in this paper.
in some sense, that's a harder problem than melting them.
Well, I'm not sure. I think both are very hard problems.
Okay.
The first one, there have been lots of proposals. I described them, or I list a few in I think the first, maybe the second paragraph of this paper. I just run through the
Yeah.
list of
Johnson,
contenders.
2017, impact generated vapors, radiation.
Yeah, shock waves, stellar flares,
Yeah.
even lightning in the
Okay.
Proto Nebula has been proposed. Um, this work was really inspired by a talk that Sarah Stewart gave
Okay. Hmm.
several years ago, talking about a possible melting mechanism, asteroid collisions. So
Good.
back in the day, asteroids smashing into each other at speeds, super kilometers per second speeds approaching 10 kilometers per second, if not even higher,
Hmm.
vaporizing collisions that can also produce melt.
Hmm.
And in that seminar, that very nice seminar that she gave, she also talked about the second problem,
Okay.
uh, how to recollect these droplets in the aftermath of the explosion,
Yes.
how they might come together again. And that really struck me, I have to say, because I thought, I mean, the sign seems wrong, right? I mean, you exploded the thing. So how do you put Humpty Dumpty back together again?
Exactly.
Yeah.
Good
So, okay.
shout out to Sarah. Good shout out to Sarah.
So yeah, it was really a very inspirational line of thinking. So maybe I'll just cut to the chase and talk about the idea that I'm proposing here.
Okay.
Um, the idea is, well, it's pretty simple actually. So imagine, and it's not specific, I should say, this collection mechanism that I'm proposing is not necessarily specific to collisions. It could
Okay.
happen, say, downstream of a shock, and
Okay.
it as well.
Yeah.
All I really am imagining, where I'm starting, what I'm starting with is a vapor of silicates and metal
Okay.
that's condensing.
Okay.
However you want to melt it,
Sure.
that's up to you.
Okay.
I like collisions. In particular for this particular class of chondrite called CB and CH chondrites, which my understanding having delved through this immense literature and talking to people, I get a sense, and people will email me, I guess, if they disagree, but I get the sense that there's a consensus, dare I say, an agreement in the community that these particular classes of chondrites really did form from a collision.
Okay.
Okay, but putting that aside, regardless of whether you think the melting was from a shock or from lightning or from stellar flares or from a collision, I'm this paper that that I wrote, this one, uh,
Mhm.
is sort of agnostic about that. All I really am interested in is a vapor. So
Okay.
however you melted it, um, silicates and metal, and it's cooling now.
Yes.
It's on its way to condensing, forming melt droplets out of that vapor,
Yes.
these chondrules, and maybe also metal nodules, that the kind you find in CB and CH chondrites.
Uh-huh.
So, and the idea, I hope I can can do justice to its simplicity because it's a very simple idea. The idea is as this vapor is condensing,
Okay.
uh, if you imagine seeding it with some temperature fluctuations, so it's not completely uniform in temperature. I think that's completely unreasonable, right? To imagine that it's just strictly uniform temperature. So there are regions of this vapor, this cooling vapor. Some regions are a little hotter, some regions a little colder.
Oh, I see where this is going. Okay.
Yeah, right? Can see
Going.
where this is going.
Keep
The
going.
colder regions will have less pressure
Yeah.
because they're condensing. When you convert the vapor into liquid or solid, you lose vapor pressure. The
Hmm.
saturation vapor pressure is exponentially sensitive to temperature. So tiny little fluctuations in temperature will give rise to, larger amplitude variations in the degree of saturation. The cooler regions will be condensed more. They'll have more particles in them.
Yes.
They'll have less pressure also, and so they'll tend to uh, compactify, to collapse under the pressure of the less condensed, higher pressure surroundings.
Hmm.
So imagining that this gas is fragmenting, it's condensing inhomogeneously.
Okay.
There are pockets of it
Sure.
condensing first and getting crushed under the pressure of the surrounding slightly hotter regions.
Hmm.
And in these pockets, I I call in the paper I call them bubbles, but just pockets, slightly cooler regions. Um, as they're compactify, as they're collapsing under the pressure of the surrounding medium, they can entrain those particle condensates, including chondrules, and bring those little solids into a smaller and smaller volume.
Okay.
So people maybe, this reminded me a lot of George Field's thermal instability,
Yeah.
right? So creation of a two-phase medium
Hmm.
where you have cool, dense gas surrounded by a hotter, less pressure medium.
Cool.
And the cooler regions, when they collapse, they can train those solids, and you can compactify the whole thing all the way down to conceivably solid density to reconstitute these planetesimals.
Okay. Okay.
Okay, or at least bring the particles to a density high enough for some other process to take over, like self-gravity,
Oh, sure. That,
right?
yeah.
To bring them together,
Hmm.
get into it to create a competent rock. So that's the idea.
Love
That's
it.
the
Love it.
that's all it is. Oh, and I should also say, the reason why there might be an instability, that this collapse might actually occur exponentially fast.
Implosion. Hmm.
Yeah. Is because these particle condensates, the condensed liquids and solids, they radiate a lot more efficiently, right? It's everyone knows particles, dust particles, liquid or solid, if it's condensed, it'll just radiate like mad,
Crazy.
radiate much more efficiently than the vapor, which can only cool through lines. So these particles, they lose energy by radiation. So if you have this slightly cooler region filled with particle condensates, those particles will radiate away their energy and cool that pocket even faster.
So it's a runaway process.
Yes, that's what I'm proposing, that there's an instability
Okay,
in this condensing medium.
cool.
Okay. So, and what we did, what I did not do a formal stability analysis. That's what I'm working on now. And we can talk about that maybe after I present the results of this
Sure.
paper.
We'll
But
come back to
for
that.
this paper, what I did, and um, I'm very proud of the word choice that I use. I thought about a long time. I thought for a long time. I mean, I'm basically just addressing sort of or solving a little toy problem in this paper. And the word I finally wound up using was rig. Sorry, I pulled
Rig.
it
Okay.
from our contemporary
There
politics.
it is.
So right there, instead, in this preliminary study, we rig up bubbles
Yes.
that can collapse.
Yeah.
Okay, so
Yeah. Yeah. You're putting them right on the edge, right? And then let it go.
yeah. I'm sort of I'm making all kinds of optimistic assumptions
It's
that the bubble can continue to cool to its surroundings, that its temperature is less than the background radiation temperature.
radiating.
Not going to worry about what the background is doing. I'm just worried about what this little pocket, how this pocket, I'm gonna arrange conditions for it to collapse, and then I'm just going to see how it collapses.
Uh-huh.
Time scales, how the optical depth increases,
Does it bounce?
speeds with which it collapses. I can't collapse it too fast, otherwise all the particles within it will just crash into each other and they'll shatter, right? So I need to sort of have the bubble collapse at a gentle enough rate to have all these little chondrules within it settle into a nice, coherent, competent sphere.
Cool. Very good. I'm with you.
Okay, good. And I call this shorthand, the shorthand idea for this I call cavitation.
Mm-hmm. Mm-hmm.
Right? It's just like cavitating bubbles that
Mm-hmm.
you find here in terrestrial phenomena. Uh,
Shrimp.
yeah, around propellers for submarines, for example,
Yes.
you'll get bubbles of water vapor which
Mm-hmm.
collapse under the pressure of the surrounding water, and that collapse can be really uh, powerful. It can
Yes.
exert high pressures. The stresses involved with the collapsing bubble can be so high in terrestrial, around underwater machinery that it can actually chip away, right, at the metal
Mm-hmm.
of the ships. Uh,
Mm-hmm.
this is well known. So the collapse can occur on as fast as the sound speed,
Dynamic. Okay.
sonic collapse.
Mm-hmm.
Um, in fact, I think there can even be like light emitted.
Yes.
Uh,
Some cases.
Sonoluminescence, I think, has
Yes.
been talked about as well, right? Um, Sometimes you get these bubbles from the pincers of these marine mammals. They can
Yep.
have a little flash. It's like they
Mantis.
snap their fingers and then this bubble collapses and it creates a little flash. Um, so it can be quite dramatic, the collapse.
It can also
I
generate.
find solutions here. It's very natural for the collapse to be sonic. I actually need to slow it down because if the collapse at sonic velocities, kilometers per second, or even, an order unity fraction of that, that's too fast.
Right.
The little babies, if they crash into each other at kilometer per second velocities, they'll shatter.
Mm-hmm.
So that's no good. I need to slow it down. And I can do that. I can regulate, or one can regulate the collapse speeds of these bubbles by uh, the rate at which the bubbles collapse can be regulated by the radiation.
Okay.
Right?
Okay.
Radiation emitted by the bubbles depends on how optically thick the bubbles are,
Yes.
and I can slow it down to the point. I can slow it down arbitrarily depending on the optical depth of the bubble.
I'm with you.
So that's the basic idea,
Cool.
and I hope that's reasonably clear. Maybe we can jump to a figure.
Yeah, figure five.
Yeah, figure five is the one which
Money shot.
had previously suggested. Might be um I don't
Okay.
know, the money shot. I don't
Capitate.
know how much this is worth, but
I'll give
it
you a nickel.
I
Okay.
created this figure in the summary section of the paper to sort of summarize the whole idea. And the other figures in the paper, they're quite similar. They're just sort of simpler versions of this summary figure.
Okay.
And
Yeah.
since it's a summary figure, I do apologize. It's now that I look at it again, it's kind of busy. I've
That's
got
very
like
cool. I mean,
all sorts of
it's
different curves. I've
all the
got two
information.
axes going on. I've got four panels. So, but just take you. I'll try to do it reasonably uh, pedagogically. So if you just look at the first panel, the
Okay.
top left panel.
Mm-hmm.
Okay, top left panel. Um, the region I'm thinking about, I'm free to choose the scale. And I'm
Yes.
imagining a
Yes.
bubble that's about a kilometer in size. So the R is the radius of the bubble, and
Okay.
it's plotted against the left-hand axis.
Mm-hmm.
Okay, so kilometer versus, I'm sorry, R in kilometers versus time. I start with a kilometer-sized bubble. Start with a kilometer-sized bubble, and you see it as it shrinks under the pressure of its higher pressure surroundings.
Yes, initially.
And this particular evolution that I'm showing, the bubble shrinks by something like 2 orders of magnitude in the course of about 10 minutes.
Okay.
Okay. And then the corresponding velocity of the bubble, r dot, that's plotted against the right-hand axis.
Yes.
So
Mm-hmm.
that's in meters per second.
Okay, I'm with you.
And I've chosen parameters for this bubble so that I don't smash the little chondrules into bits.
Okay.
Okay,
One
so 10 meters per second, I think is okay. 100 meters per second, I think that's a little dangerous.
stretching.
We'll get varying views on this in the literature. Some people say, oh, even 200 meters per second might be okay. Anyway, I'm trying to play it a little bit on the safe side. 10
Papers.
meters per second, it's still pretty fast.
Mm-hmm.
But for competent solids, I think we're okay.
Of course, one of the standout features in these evolution curves is they oscillate.
Yes, so that's a very natural consequence, right? Because without the radiation, if you forget about it's the radiation that's allowing it to lose energy secularly and shrink. But
Yes.
if you just turned off that radiation term,
Okay.
then it would just oscillate. It's just the pressure. It's it's a little region
Ah, ah,
of gas, and if you squeeze on a little bit,
ah.
it'll get higher pressure and then just bounce out. And it just rings. It's just the P mode. It's just the pressure oscillation. It's
I'm
just
with you.
acoustic oscillations of a bubble.
Very good.
All these little oscillations on top, they're just acoustic oscillations,
Mm-hmm. Mm-hmm.
where the period's measured in seconds. And it's just a sound crossing time
Of the bubble.
across the
Yes.
bubble. That's all it is.
Cool.
Yeah,
Very
that's all it is. But you see, on top of that, there's this gradual decline on the scale of, in this case, about 10 minutes. And that's regulated by the energy loss from radiation from these particles that are embedded within the bubble and losing energy by radiation,
Mm-hmm.
cooling off to the environment.
Mm-hmm.
Okay, so that's the first one. That's all it is. Um,
Interesting concept.
maybe what I can do is I can go to the bottom right panel.
Okay. Over here.
Okay. So for the bottom right panel, I'm putting little test particles inside this bubble.
Okay.
Okay. And the particles, solid particles, um, they have different sizes.
Okay.
So the different colored curves correspond to different size particles.
Okay.
So the black curves correspond to particles. I mean, real honest to goodness, like solid particles at 100 microns. Not that different from chondrules.
Mm-hmm.
Okay, so 100 microns, I go factor of 10 bigger, a millimeter.
Yes.
I get another factor of 10 bigger, a centimeter. That's the orange curves.
Yes. Wow.
Okay,
Curious.
so I put these little test particles, solid particles, inside the bubble. At first, I put them all at one of two locations, either at 25% of the, so here's the total bubble. Okay. Well, here's the center of the bubble and here's the edge of the bubble.
Okay.
Okay. And then I put a set of those particles at 25%
Okay.
of the total radius, and I put another set at looks like 75%. These are just
Okay.
test locations. I'm just embedding them
Oh,
there.
I see.
That's
Yeah,
where I
yeah, yeah.
start them.
Right here. Yep, yep.
Exactly, at time zero.
Mm-hmm.
So
Okay.
RC is just the position of the C for chondrule or
Okay.
condensate. Um, and I just embed them there.
That's
Okay,
fine.
start
Okay.
them off. And then I just ask, okay, and then it's just a drag calculation,
Yeah.
right? As the bubble is, the gas is ringing and also shrinking at the same time, I track where how the particles move relative to the gas.
Mm-hmm.
Do they follow the bubble gas as it, oscillates and shrinks down, or are the solid particles
Fine.
decoupled from
Okay.
the gas?
Okay.
Right? You can imagine if they're too big, then the drag won't be enough. The gas drag won't be enough
Right.
to drag them in as the bubble is collapsing. They'll just be left behind.
I'm
And that's what happens for the particles that are too big. And too big turns out to be about a
about
centimeter,
a centimeter.
about a centimeter. So
Uh,
things that are bigger, and I didn't bother to plot 10 centimeters because it's even worse for, anything
more.
larger than that, they leave the bubble. So you notice I'm plotting the dimensionless quantity RC over R.
Mm-hmm.
So outside is, RC over R greater than one. So once it gets above that dashed horizontal line,
Lost.
you're gone. You're no longer, the bubble has left you behind.
Exactly. Yes.
Yeah,
Yes.
the bubble has left you behind. But if you're small enough, if your surface area to mass ratio is large enough,
Yes.
then you will be entrained.
Okay.
Uh, and that's what happens for 100 micron or smaller or millimeter size things also get entrained.
Millimeter.
And
Okay.
they actually settle. They sort of gravitational, not gravitationally, but they sort of settle closer to the center of the bubble, even as the entire bubble shrinks
Right.
down.
Right.
So I
Okay.
thought this was an encouraging result,
Yeah.
because chondrules, metal nodules in chondrites, they really are this size, right? Millimeter, 100 microns, and it depends on the gas density, of course, but that is not really a free. I mean, I wouldn't call that a completely free parameter for me because it's set by the saturation vapor density,
Yes. Okay.
right, at 2,500 degrees Kelvin for
Okay.
silicate vapor.
Okay.
I'm not just making up this density out of nowhere. I mean, I'm
Oh,
asking, okay, if I have a gas of vaporized silicates, what is the pressure? What is the density? And I'm starting with that.
okay. Good.
And very naturally, it selects out 100 micron millimeter size things.
Okay.
Okay,
Okay.
so that I thought was
That's yeah, very.
an encouraging result.
Mm,
Um,
very.
Yeah, and the rest of the panels, I mean, you can sort of read them. Maybe we can go up to the yeah, to that one, the top right. Okay. So this is plotted. The top curve is hey, we could look at tau, sure. Tau is just the optical depth.
Okay. I'm just checking.
Tau is just the optical depth in solid particles. The gas has no optical depth,
Okay.
not in the continuum anyway. So this is just the continuum optical depth. It's really just the geometric optical depth of the bubble. It's all these particles. I'm keeping track of how many particles are condensing. And so you can just see the bubble just gets up thicker and thicker.
Very cool.
The bubble just gets thicker and thicker. And I don't have to start. I noticed I started pretty thick. I started at an optical depth of 20. If you look at the other figures, which we don't have to, but just for the reader's information, I can start with no solids at all and
Right.
get very similar results. I can start with, optically thin bubbles, but eventually all roads lead to optically thick as I condense more particles and as the bubble shrinks.
Yes, it must.
Yeah.
Okay.
Okay. And then M solid over M, I mean, I hope that's clear. It's just the fraction of the mass of the bubble that's solid.
Mhm.
And that's plotted against the right-hand axis in blue.
And it's curious
Again,
that.
for this particular run, I decided, oh, I'm going to imagine that already had some particles to begin with. So I started with what it looks like something like 30% or something,
Okay.
1/3 solids, but eventually it all becomes completely solid.
Right. And most of the mass going into solid happens fairly early in the evolution, right? It saturates fairly early.
Yeah, yeah, maybe half, yeah, uh,
Hmm.
200 seconds or so, 300
Yeah.
seconds.
Yeah.
You have to, I do worry about that, because that is a concern. I'm glad you brought that up. It's a concern because the bottom panel, which we had just reviewed, I'm treating the solids as test particles,
Uh-huh.
right? That that are slaved to the well, that obey that follow gas drag, right? Where the bottom panel, in other words, assumes that the gas density exceeds the solid density.
Ah, okay.
Yeah, right?
Yeah,
Because
yeah.
the solid particles are treated as test particles.
Right.
But
So massless
if
test
this,
particles? Massless test particles, or these test particles have mass?
well, these test particles definitely have mass,
Okay.
right?
Just
But
checking.
there's just no back reaction.
Yes. Okay.
There's no back reaction from the momentum of the solids to the momentum of the gas. That back reaction I am neglecting.
Okay.
But that drag back reaction, that momentum back reaction,
Hmm.
will become important as M solid over M approaches unity.
It's larger. Right.
Yeah. So
Right.
that is a shortcoming,
Okay.
one of many shortcomings of this calculation.
It's something for the future, which we will come to. Yes.
Yeah, yeah.
Cool.
Okay.
Okay.
So yeah, again, I don't need to start with M solid over M. I can start with M of a third. I can start with no solids, just a
Yeah.
complete gas and cool it, and I'll just just create the solids that way.
Okay.
So anyway, this is just a one particular scenario which we're looking at, and just to complete the story, I guess we can look at the bottom left
Thermo
panel.
thermodynamics going on down here. Okay.
Yeah, and this is, I mean, it's just density, temperature, and pressure. I'm just, tracking of the bubble relative to the background. Uh, One thing I will note, I think, is if you look at the black curve, which is temperature, that's what it's doing. That's the temperature inside the bubble.
Yes.
That's what it's doing. And then I rig the background so that the background radiation temperature stays below TT.
Lower. Right. And
And
here
I
we
need that because I need the bubble to lose
lose
photon
energy.
hours.
Otherwise, it's not going to go down.
Otherwise it's not going to shrink.
Yeah,
So
yeah.
that's the other shortcoming of this paper, which I hope I'm reasonably clear about in the paper, that one really needs to do this self-consistently in a future work.
Sure. Sure. But
For now, I'm just keeping I fix the radiation temperature of the background to be lower. It's a few percent lower than that of the bubble, so that and then the bubble just loses radiation on the time scale. It turns out about 10 minutes.
so that it collapses. Yep.
So that
Okay.
it collapses. Um, okay, so I think I'm not sure there's any really need actually to look at the other figures. I hope the picture is reasonably clear.
Clear to me.
I will say maybe the last statement I might make, I've been pointing out problems.
Hmm.
Um, Another problem, um, and this came out when I shared the draft with colleagues. They said, "Well, how big of a planetesimal can you make?" Well, I said, "Well, that depends on how big the bubble that you started with."
Here it was a kilometer.
Here it was a kilometer, and if you take this kilometer filled with saturated vapor pressure and you condense it all and compactify it down to solid density, I would form a rock that would be about 10 meters in diameter.
Okay. Okay.
Okay, 10 meters filled with these little, millimeter and
Yeah.
100 micron size things or smaller.
Hmm.
10 meters. And people said, well, that's nice, but it's a little small. And they were being polite.
Nah.
It is way smaller. 10 meters is a far cry from the parent bodies of chondrites
Yes, that'll
They're
be fun.
thought to be on the order of 100 kilometers across.
Okay.
And this was very interesting for me to learn. People infer this, the sizes of the parent bodies to be 100 kilometers. So when
Yeah.
the rocks, right, when the chondrites fall to the ground, I mean, they aren't, I don't think they're much bigger than a meter or something, right? I mean, they're sort of this size or for size of a bread loaf or something, right? But those are thought to be chunks
Of the original parent.
from an asteroid,
Yeah.
presumably filled with chondrules, um, that was about 100 kilometers across. And that constraint comes from the degree of thermal metamorphosis in the chondrite,
Okay.
because you need to take these chondrites and you need to sort of bury them. When they were part of the parent body to begin with, they had to be buried at considerable depth, at a depth of on the order of, dozens of kilometers. Um, and you need to have some live aluminum 26 to heat this thing and
Iron
produce
60. Or iron 60. Aluminum 26, not
okay,
iron 60.
okay. Yeah, but it needs to be done at depth because if
Mhm.
you, yeah, to sort of retain the heat over long enough to
Yes.
change well, to thermally metamorphose the rock.
Yes. Okay. So instead of starting with a 1 kilometer cloud, why don't I start with a 1,000 kilometer cloud?
Yeah, right, right. So yes,
How bigger?
that I think is another direction to go, and maybe
Okay.
behind the shock front in a protoplanetary disk,
Yeah. Okay.
size scales can be, that big easily.
Hmm.
So yes, that is a direction that I'd like to pursue. The reason I chose a kilometer here is because I was thinking really about these CB, CH chondrites,
Yeah. Hmm.
right? Where I'm
Okay.
imagining that this fragmentation, this instability, this compactification, these bubbles occurring inside a vapor, inside a impact plume,
Okay. Okay. Yeah. Yeah.
right? And if the bubbles are too big, they'll get sheared apart by this impact plume, which is expanding.
Yes.
Right.
Did melt them.
Okay. So, and interestingly, okay, so the people who told me about the thermal metamorphosis constraint, that applies to a very particular kind of chondrite. Um, well, I think the majority of them actually, the ordinary, I think it's cited in the text. Maybe we can go there. I
Sure.
forget the classifications. It's just this literature has been very difficult for me to parse over the years. I'm
Okay. It's all
making
good.
progress, but I'm still
So
learning the
CB.
jargon. It's sort of at the end, towards the end. So the last
Okay.
paragraph of the paper.
The intro.
Very last paragraph of the paper.
Oh, of the paper.
Last page.
Yeah, yeah, yeah. Okay, I'm with you. I'm with
Uh,
you.
so
Boop,
this constraint,
boop, boop,
okay,
boop, boop, boop. Pros and cons. Yep. And there's our.
pros and cons, okay. This is a con, although it could be a pro. We'll see.
We'll see.
So, yeah, this constraint of hundreds of kilometers across, you can see I cite it here. It applies to ordinary and enstatite chondrites. Okay, so HLLEH. Um, so I have a problem there. And I think the majority of chondrites, as far as I understand, I guess that's why they call them ordinary,
Yeah.
because that's the majority.
Okay.
However, the CBs and the CHs, okay, which were really, if I say I'm agnostic about the melting mechanism, but as far as I can tell, people really, really like asteroid collisions for CBs and CHs. For those, right, I really did need my bubbles not to be too big.
Not to be, yeah.
Yeah, because if they were too big, they fill the entire plume, and the plume, meanwhile, is shearing apart and expanding, and I it's hard for me to compactify. This is really a local instability that I'm talking about.
But on the other hand, you might expect a whole distribution of cloud sizes.
Yes, 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 yes. But
Mm.
the last thought I wanted to share with folks is I said, okay, you have this constraint of 100 kilometers for the ordinary and enstatite chondrites. Okay,
Hmm.
I have a problem there. However, what about for the CBs and the CHs? And I couldn't get an answer from anybody. And I did Google searches and so forth. I couldn't really find a constraint on the parent body sizes for CBs and CH. I don't know. Maybe
If you know, get in touch
maybe
with.
they're much smaller. Maybe they're 10 meters. I don't
Ooh,
know.
ooh. So if you
Okay.
let
So I leave that out there as a possibility that maybe the parent bodies of CBCHs are systematically smaller than for ordinary adenstatite. Although I'll say another thing.
okay.
So many people at your institution, uh, I think can speak to this. I learned from a seminar the other day. Oh, Elkins Tanton
Sure. Lindy.
talked about psyche
Yes. Yes.
and how it could be the progenitor of CBCHs.
Okay.
And psyche's big.
Oh, it's actually big.
Psyche is not 10 meters.
Uh,
So psyche's way bigger than that. So if the parent bodies of CBs and CHs are as big as psyche, then I'm in trouble again.
trouble with this scenario, at least
Yeah. Yeah.
anyway.
And people tried to cheer me up. They said, well, you form these 10-meter size things and then you just have to collect them all, collect all the 10-meter size things, right?
Yeah, there you go. There you
To a
go.
larger body.
Let self-gravity do its thing.
Yeah, well, something. There's another collection mechanism.
Hmm.
Yeah, so that's where the field stands. You asked at the beginning of when we were prepping for this interview, whether there's a future for this subject. And boy, is there a future. There's so many unanswered questions. Um,
Okay.
and this I'm putting this out there as one collection mechanism. But I think there's obviously, I think, a lot more to be done here.
There's a lot of gas in this one. Let's put it that way. Right? There's a lot of opportunity.
Not gas. Vapor. Yeah, the
Vapor
vapor.
gas in this
The
one. Yeah,
vapor.
very cool. Very cool. Well, Eugene, I want to thank you so much for walking us through your very awesome APJ letter. That was beautiful. Very nice. Good toy problem. And so let's go ahead and get into it a little bit. So you mentioned it a couple of times on future directions, and I'm wondering what you think is the most immediate things to go after besides convincing your colleagues to take different approaches on it, or similar approaches to it. So I think
Yeah.
you're working on thermal instability as your next one, and so
Yeah. Well, I mean, it's doing this problem better.
yes,
I arranged these bubbles to collapse and just wanted to see, well, how would it go and what would be needed. But what one should really do, and what we're doing now, this is with a student at Berkeley, Stefan Chan,
okay,
I'm making headway. And it looks
cool,
actually, at least last week, it looked okay, um, to do a linear stability analysis.
yeah, hmm,
Yeah.
very nice, very nice.
Yeah. No gravity, just
Yep, it's
just
thermal.
cooling.
Hmm.
Um, so we need an energy equation, right?
Yes.
Adiabats are no good.
That's
So
a problem.
adiabats are not welcome here. You need a real honest to goodness energy equation, and we're just going to perturb it with radiation. You can do this pretty easily in the optically thick case. You just model the radiation as a diffusive term.
Right. A little
In
harder in the intermediate regime. Optically thin is easy. It just disappears.
Yeah, although, but then you have these different regions, right?
Hmm. Yeah.
And so each of them is collapsing and putting out radiation, but then from a given bubble, right? Then you're receiving the radiation from all these other bubbles.
There's the interaction of the bubbles. Right.
Exactly. So it becomes, in the optically thin case, I sort of worry about the global nature of the problem, right?
Sure. Because
It
that's like,
stops for me becoming a local instability anymore. And then you sort of have to worry about the global dynamics. So
right.
I haven't quite figured out exactly what to do there.
Okay.
But at least in the optically thick case, I think it's still local. And one can formally derive a dispersion relation for perturbations,
Nice.
medium, which is cooling, condensing, forming particles which radiate, and we are pursuing that right now. So that's the immediate next step.
Cool. And this is all this work is analytical, quasi-analytical.
Yeah, yeah, yeah. In the end, we get like these polynomial dispersion relations,
Uh-huh.
and then you have to find the roots, right?
Yes.
And cubics are bad enough.
Oh, I love cubic. Cubics are
I
great.
don't know.
Cubics are great.
I've written down analytically so I could get the roots to a
Well,
cube.
they do a little more work than square roots, but they're
Yeah, so it was pretty annoying. But
it's a good thing you didn't have a quintic.
yeah, I know. I count my blessings. But so yeah, semi-analytic.
Any thoughts or directions or encouraging other people to pick up and do numerical work on it?
Yes, yes. So the numerical work initially done by Sarah was the impetus for all this whole line of thinking. And so looking at that dynamics of the impact plume with radiation,
Oh,
with
anything you throw at it. Yep.
yeah, which was not, I think, included in the original simulations.
Mhm.
Um, there was another maybe a technical point, but those impact simulations that Stewart and Carter had conducted, there was ambient hydrogen
Ooh.
in the so you have these two asteroids colliding together in a
Yeah.
sea of this protoplanetary disk gas, hydrogen.
Mhm.
Um, they used the hydrogen to actually recompactify this impact plume. So to implode back the impact plume from the pressure of the surrounding hydrogen.
Okay.
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 I think that, and I've said this in the papers that we've written, I think that implosion, I think, is exaggerated because they assumed that the collision happened in a static, and a essentially static H2 gas.
Okay. Yes.
Okay. But in
Uh-huh.
reality, these rocks will be colliding on highly eccentric orbits.
hmm hmm
Highly eccentric, the gas could be moving on circular orbits, but because the rocks, the asteroids that are coming together will be moving on inclined and eccentric orbits,
Yes.
the impact plume will be barreling through and have a large relative velocity
Come.
relative to the H2 gas.
Yeah.
And so, re-imploding it with, there'll be a strong headwind, is
Fair
what I'm
enough.
saying, from the hydrogen. And I think I would like to see that headwind more realistically modeled.
Okay.
Okay.
Cool. There's a challenge, folk people. Go for it.
Yeah, I'd like to see that hydrogen nebular headwind more realistically modeled. And what exactly does it do to the impact plume? I would bet, happy to be proven wrong by the numericists, but I would bet that it doesn't actually implode or recollapse the impact plume. I think it'll try to run through the impact plume, and actually it'll be more destructive than anything else. I think it'll disperse all the particles. I think it'll make the problem worse,
Believe it.
is what
hmm
I think.
Okay.
However, the experiment will be the arbiter of this. So I would encourage those experiments.
Spoken like a true theorist. Spoken
Yes.
like a true theorist. Oh, well,
I
experiment
don't
is
know.
the
Seems
ultimate
like a
art.
bit of a
And
cop
you're
out,
right. You're totally
actually.
right. This is an observational experimental science. So, yeah. But cool. Well, it'd be really fun to see this develop over the next couple of years. As people, and right or wrong, right? It's an idea, and so follow it up, right?
It's so, I mean, it's such a compelling problem. I don't know. I mean,
Yeah.
eh, these
That's always
80% of the rocks that fall to the sky are filled with these things. So what the hell?
true.
Sorry, pardon my French.
Mhm.
But what's the origin of these things?
Exactly.
Uh,
Exactly.
it's
Yep.
so it's just so mysterious to me.
And it's been a mystery for a while, so it's a good problem to go at. Really good. Very cool. All right. Eugene, I want to thank you once again for walking us through your very awesome APJ letter.
Thanks, Frank. I really appreciate it.
Well, thank you. And that will do, everyone. And I hope this made your cavitation astronomy day just a little bit better. And we will see you on the next one. Bye bye.
Bye.